So the next talk will be presented by Holger Boche. He did his PhD in Dresden in electroengineering, but also in mathematics. Afterwards, he was leader of the Fraunhofer Institute in Berlin, and since 2010, he is professor at the Technical University of Munich. He won several prizes like the Johann Philipp Prize or the Gottfried Wilhelm Leibniz Prize, and he supported the EACN since the beginning of the series of workshops. He was there at the first one, which was during Corona, until now the fifth one, and we are happy to have you here again, even if you cannot join in person. And this time he gave us some insights about uncomputability of quantum gate circuits emulation. So the title of the talk is Feynman meets Turing. So Holger, the stage is yours.
Yeah, many thanks for having me. So Christian already explained everything. So this is a joint work with Yannik from Munich, Zoe from the Sorbonne University in Paris. So we also have a connection to France, and with Frank from TU Dresden. And the motivation for this research direction was very clear that in Munich we have this Munich Quantum Valley. So although Bavaria is a very small, tiny country in Europe, still we have the ambitious goal to build a Bavarian quantum computer, and it seems that this task is not so easy, and I will describe why. Okay, and then also connection to the Quarks project, so quantum and networking computing. So there are 3 dots on my slide, on the Quarks projects, and these three dots correspond to 3 quantum processors that we have. Okay, but first I will start with the motivation. So quantum computing is a very interesting topic. And we all think that this is a very new topic, but actually it's already very old. So since 1993, since Shor's very famous paper on factoring integers on a quantum computer, that this is an extremely easy task. We know that quantum computing can be very powerful. And since then, the people tried to build a quantum computer with limited success. So computing is, of course, so in general, you may think that computing is a very simple thing, but of course, the opposite is true. Computing is a very challenging thing, and it's deeply rooted in mathematical logic, as we will see. I will start with the motivation. So what is computer science? Yeah, computer science as a discipline was defined in 1989. And computer science as a part of science is the science of automated problem solving. So the question is, the whole question behind computer science is to find algorithms that are possible to run on, which run on certain machines, usually Turing machines or digital computers, and we want to solve for a class of problems. We want to find an algorithm such that if we have a problem in this class as input to the algorithm, then the computer should compute, or the algorithm should compute the output as an output the solution of the problem. So this is all behind. That's the only thing behind computer science and computing as a discipline. Now, let's try to look at the quantum computing problem from this point of view. And I have to be honest, I think that not many people have looked at quantum computing from this point of view. But at the end, if the people in the physics community, if they are able to, deliver a quantum processor, as you see here, yeah, so if we have once a quantum processor, which is able to run, a certain number of quantum gates in a certain way, then of course the question is, how can we control this quantum computer? and how can we put practical relevant problems on this quantum computer such that the computer is able, or this quantum processor, so actually the quantum computer is the whole thing here, such that the quantum processor is able to solve the problem. And here comes exactly the interesting problem, because, and I have to say, everything that I will describe is relevant for quantum computing on quantum computers which are based on quantum gates, and that's the main that's the main approach of all the companies that we know. So it's very simple. So the quantum computer in total is this large box here. It consists of the quantum processor and then all the control logic and all the software or the processors here around this quantum processors. So usually we start with a real world problem. So factoring an integer because we want to break RSA, or solving interesting mathematical optimization problem. And this real world problem has a mathematical description. So of course, the integer factorization is already here part of this description. But of course, this description is still in a certain language, and our quantum computer is not able to understand this language. So of course, we as a user, we have to put this onto this quantum computer, and the mathematical description is just the input of the quantum compiler. And the quantum compiler, of course, computes at the end the machine instruction of our quantum processor and the initial state, such that hopefully after classical post-processing, the quantum compiler is also, of course, controlling the post-processing, the whole system computes a solution, which is the solution of our real-world problem, like factoring a number, integer, or the spatial structure of a protein or something like this. So this is the whole problem. And I have to say, most of the people in the physics community are only, concerned with this quantum processors, and they assume somehow that all the things here around this are easy to solve. But of course, here we already see we have a certain, discrepancy between the description of the things. So we have here the mathematical objects, and here this here are these machine instructions, and you can actually think even on a classical computer. So of course, if you work with the classical computer, you never except you have to optimize the running time or something, complexity stuff or something. You never work with the machine instructions. You always have a high-level language like C, and then you have a compiler such that if any program in C is translated for the machine into an execution table such that the machine is able to run, the machine instructions in the right way, such that at the end, as a black box, the machine is solving your problem. Okay, so this is a very simple problem. And actually, for a classical computer, digital computer, that's not a big deal. But for a quantum computer, it's somehow a little bit different. And what we want to do is, so everything here, this description, everything that we do in mathematics is, of course, written in a mathematical language, and is, of course, we have to put it in such a way that it is machine readable, like the coefficients, everything that we have to choose. So everything here is, of course, digital hardware in the traditional gate-based quantum computing approach. And the question is, okay, can we translate all these things? And actually, what we want to do is, we don't want to analyze this problem in full generality here in my talk because of time constraints. Actually, I will start with a very simple question, the question of circuit emulation. So just assume that you are company B, like Google, and then you have another company like IBM, and they have a different gate set. And they publish something in Nature or Science, take any of these journals, and you don't trust these simulations. And what can you do? The only thing that you can do is just run the same experiments on your own hardware with a different gate set. That's the point, And usually they have to choose different gate sets, I guess, because they want to circumvent the usage of certain patterns and so on. So this is, of course, in a classical setting. This is very simple. That's a trivial question. So for a classical computer, it's very simple. You have a Boolean function here. Yeah, you have a Boolean function, and then you have a certain set of logical gates. But at the end, you have here a different set of logical gates. And of course, you can use different sets of logical gates because you have a lot of redundancy between the logical gates that we know, and they are complete, of course. And that's also what we do in practice. So in practice, we never implement all logical gates on a circuit. We only implement a subclass. Yeah, because for this, we know very efficient implementations. So, and the problem, you're given a circuit to run this on your own. Reduced circuit set is, of course, a very simple task, can be solved algorithmically, and is Turing computable. So maybe I should go back now. That's so you find a program doing this. So the complexity, so if you ask what is the complexity of this is a little bit a different thing, but also not so difficult because you can take lookup table and so on. So now we want to do the same thing for the quantum computer. So again, so assume here, everything here, this is the description of the IBM gate-based quantum computer. And then here we have the Google-based quantum computer. And then we want to simulate the IBM gate-based quantum computer on a Google-based quantum computer. Can we do this? Yeah, is this possible to solve in an automated way? Yeah, we are looking for a program which gets input here, the algorithm, the quantum algorithm on the IBM machine, and the gate set of the IBM machine, and then we want to run this on the Google machine. Okay. So for this, of course, we have to formalize. What's the language? And of course, the language is only, the language of a digital Turing computer or Turing machine. The good thing is, of course, and that was exactly the point where Turing invented the whole concept of a Turing machine, and then, of course, was also the father of computer science, that, we can represent all the interesting things, practical problems that we want to solve. We can implement this on the Turing machine. So, for instance, we need, of course, computable numbers. Not all numbers are computable, but the most important numbers like P and E and square root of 2 and square root of 5, yeah, all these numbers are, of course, computable because we have algorithms for these numbers. And that's exactly, so if you want to work with pi, of course, you have to give the machine an algorithm for pi, okay? Then, of course, going back, so we have a certain mathematical structure, and in general, the mathematical structure is not understandable for a digital machine, but most of the practical relevant structures, they have, of course, a computable substructure. And a function which maps, A to B is called computable if it maps the substructure A mu to B mu in such a way that a Turing machine can do the job. So you find an algorithm that you take an A here as this set as input, and the output of the algorithm is a description of f of A. So very simple thing. Formal, very important. And now it's clear we only can work, so any gate-based Turing machine can only work, of course, with unitary matrices. We, of course, have to work with computable unitary matrices because the other matrices are not representable, on digital hardware. So this is now the following thing. So we have here the gate set. We can represent here. You see all the numbers here are computable. So we can represent this on a digital hardware, and as long as we are stick to the computable unitary matrices. But here you see already a huge difference to the classical digital world. because of course the Boolean functions, they own so this set of Boolean functions for fixed alphabet lengths here also. Everything, the input size is fixed, which means the same thing as Boolean function with fixed input alphabet. This set of Boolean functions is of course a discrete set. The set of computable unitary matrices is a discrete set, but is dense, in the set of all matrices. And that's even very important from the practical point of view, because at the end you want to approximate any matrix by a computable unitary matrix. Okay, so now what is a computable unitary matrix? Very simple thing. It's just a matrix where you have for each component an algorithm to describe the component. And of course, if you want to put this U into the quantum computer, you have to put all these numbers as an algorithm, on this, or as a description, if you don't like the word algorithm. You have to you have to put this into the machine. Okay, so maybe these points are not so important. What is, from the practical point of view, very important, that of course all gates that we know, like Pauli, Hadamard, phase, C0 controls, Z, swap, Toffoli, all these gates are of course computable. And we can of course represent this. So that's not a big deal, but we already saw a small difference, or maybe even a huge difference, because the one, the set of Boolean function is a finite. So I missed this word. It's a finite discrete set, but the set of all computable matrices is a non-finite. So yeah, it's a non-finite discrete set, but it's also dense in the set of all matrices, unitary matrices. So this is now the problem, the mathematical problem formulation. You have you are looking for a function. Yeah, that's the gate emulation function that function gets as input the matrix representation of the gate. Yeah, that you want to simulate on your own machine. So this is the algorithm. This is the algorithm, the IBM algorithm. This is the IBM gate set. Yeah, and this is here the algorithm on our own not Google machine. And it's clear you can find infinitely many of these functions. Yeah. So from the mathematical point of view, no problem, of course, because there are infinitely many of these type of functions. And of course, it's also not difficult to see that that there are infinitely many functions which take computable, a computable unitary matrix as input and compute and maps this to a computable unitary matrix as an output. That's not a problem. But still, this problem is not solvable. So although there are infinitely many such functions, there is no single function which is Turing computable. And if we go back to the definition of Turing computable, yeah, this is exactly this. A function is Turing computable if there is a program which is able to implement this function. So which means in our setting that actually there is no no compiler. A compiler is always an algorithm. There's no compiler which is able to solve these gate emulation, which can emulate this gate emulation function. So this is of course I have to check the clock. This is of course somehow a little bit disappointing, but I have to say in a certain way this explains why on the algorithmic side there's so limited progress in quantum computing. So when I mean progress, I mean really scientific progress. There are of course almost infinitely many heuristic proposals for algorithms, but there are except two algorithms that I know where we have provable performance. And this is exactly Shor's algorithm. And I have to say that Shor's the only guy who really has a background in computing theory, if you look at his papers. All the other algorithms somehow have implicit assumptions about the machines and are not really algorithms. And actually, what I want to now say is I want to go to the real problem of quantum compiling. So quantum gate emulation is still a simple problem, but even this is not solvable. So the real practical problem, if you want to use it, is of course how to map. If I go back to this, picture here, how can I map here the mathematical description in such a way that I have here the right machine instruction? This is the quantum compiling problem. And of course, for the C, for machine language and C programs, it's solvable on the digital computer. But for the quantum computer, the answer is a different way. The strange thing is, of course, there is something like a Solovay. So in a literature, in a quantum computing literature, there's something like a Solovay-Kitaev algorithm. The Solovay-Kitaev algorithm gives you something like you fix your universal machine description, which means you have a universal gate set. You take as input a unitary matrix, then the algorithm or the theorem shows you the existence of a short algorithm. But if you check all the published, I have to say, proofs, if you check these proofs, then you see these proofs are not constructive. So they show only the existence of algorithm. But of course, there's huge difference between showing the existence of a solution or of being able to construct the solution. And quantum compiling is, the problem of quantum compiling is nothing else than the ability of constructing in an algorithmic way the solution, the gate set. So and even if I fix here the error, so that's also a huge difference between classical computing for Boolean functions and quantum computing, because quantum computing is per se only an approximate computing, because we only have a finite number of gates, universal gate set. So, but even if we fix, here, the small epsilon, this approximation that we want to have here at the output, we take as input any quantum algorithm that we want to run, but these are, continuous. I can select this from a continuous set. And then here I want to compute my gate that is able to approximate this matrix in this epsilon. Yeah, that's exactly the quantum compiling function. That's also not Turing computable. And in a new publication, we even showed that it's not Banach-Mazur computable. So it has really strange type of behavior. I have to say that there are infinitely many such functions, but no function is algorithmically computable. And that's why it's clear, actually, there cannot be a constructive proof of the Solovay-Kitaev theorem, because if there would be a constructive proof, I could also find an algorithm. So all the proofs that we know are non-constructive. They only show the existence, and actually there cannot exist an algorithm solving this problem. Okay, so this is so from the engineering point of view, so from the physical point of view, these are very bad results. From the engineering point of view, these are very good results, because it shows that actually quantum computing so mapping problems to quantum computer cannot automate it in an algorithmic way. And it's an engineering task. So it's really a creative engineering task to find solutions for certain classes of practical problems. And that's also, very much aligned in the world that we observe at the moment, because, the usage of hardware accelerators is, which are able to solve very specific tasks in an extremely efficient way, is very important. And to be honest, the whole idea behind NVIDIA, that's a very big, very rich, very valuable company. The whole idea behind NVIDIA is, of course, the idea of hardware accelerators. So from the future point of view, I think these results are very interesting because first they show that actually quantum computing is not trivial. Second, they show that actually it's really hardcore engineering task, very difficult engineering to find, for a given solution. Sorry, for a given problem, a solution on a quantum hardware accelerator. Okay, and that's exactly what we do in this Quarks project. So this, as I mentioned, this Quarks project is a project where the group in Dresden owns 3 quantum processors, and we are building a network with these quantum processors, and we use these 3 quantum processors as hardware accelerators for the solution of certain tasks in the network. Okay, this concludes my talk.
Okay, thank you, Holger. Other questions or comments? So, Matteo.
Hello. Thanks for the very great talk. I have some questions. So the first are a bit general. I understand that computable function, so essentially means that maybe the inputs are computable, but it could happen that the function itself is not. So that's a problem. Okay.
Yeah, that's exactly the point. And a quantum compiler would be, of course, if there is a quantum compiler, then of course there should be at least one computable function, because this function, the quantum compiler is exactly the implementation of this function.
I see. So another short thing, does your theorem apply to also infinite dimensional systems or only finite dimension?
Yeah, but if the word is already difficult in finite dimension, then you should not wait for the infinite dimensional case, because that's the easier part. But I have to say, of course, our theorem here tells you nothing about, analog quantum computing. So I think analog quantum computing is really, and maybe that's also something if you can interpret this as infinite dimensional thing. So analog quantum computing, is of course a completely different thing,
Mm-hmm.
So the bad idea of gate-based quantum computing is of course to put into a continuous structure a discrete, gate set. That's the problem.
Mm-hmm. I see. Yeah. Can I have one follow-up? So these theorems, they exclude that these functions that they exist are computable. But maybe does it happen that they are computable on a smaller subset of
Yes,
inputs?
of course, that can be possible, and that's also one direction that we go. That you that's exactly this point. If you restrict the set of inputs,
okay,
then you can.
So that's good news, right?
But it's at the moment we don't understand these type of sets, and actually, so even Peter Shor even wrote a paper some years ago and asked in his paper, okay, why is there no other new quantum algorithm except my own, the Shor's algorithm, which solves an interesting problem first. And the second is which has provable performance. Because what the people usually in physics do, of course, they simulate and then say, okay, that's the solution, but they have no performance guarantee. The idea behind all the computing is, of course, that you, at the end, because, quantum computing, gate-based quantum computing is per se an approximation. You're never able to, accept very simple problems to solve this in exactly, but you're even not able to so except these 2 papers that I mentioned, so Shor and Grover's algorithm, the sorting problem. For these 2, we have performance guarantees. For the other algorithms, nothing is known.
Thank you.
Yes, hello. Thank you for the nice talk. Is it possible to narrow down the problem of uncomputability to maybe some aspects of the quantum function, like magic, or I mean, instead of looking at the function in general, that to pin down what is difficult to compute? And is there any hope also to go to approximation instead of exact computation to also maybe relativize the statement?
Yeah, that's so that's possible. You know, that's at the moment we can say nothing about these possibilities. So the results that are presented apply exactly to, you know, quantum gate-based computing with universal gate sets. And to the question, you know, you want to emulate one universal gate set or algorithms on one universal gate set on a different universal gate set, you know, like this, you know, IBM Google problem. And of course, this is really a huge problem because these two companies, they don't trust each other, you know, because they claim that, okay, you do some wrong things. So that's a problem. And then if you develop a different architecture, then this is a different story. So here, of course, for the first part of my talk, the whole problem was that you have a digital control architecture for your quantum processor, and that, you know, all the instructions that you want to that you have to run are described in a digital way. Yeah. And for the second part still is a big problem also for other, you know, for other type of quantum computer architectures, because usually we describe our classical word, you know, in this Turing language. Yeah, that's the only thing that we know. And you cannot translate this language in any gate-based stuff. But for analog, yeah, I think for analog computing, the thing is completely different.
Okay, then thank you, Holger, for the talk and answering the questions.